Here is a new variable which is defined in the following way. If capital X is the normal variable, then another variable can be introduced here. The variable is denoted by Z. The variable is defined as capital X minus mu by sigma. Okay. So now students, one thing, please tell other people to join, because previously there were 34 students. Now I can see only 18 students are present. And this discussion is very important. You will gradually, you are going to understand when you will solve problems in signal and systems, and you will be solving problems in numerical analysis in any engineering problem. My today's discussion is very important. Okay, so please tell others to join. If capital X is a normal variable, Z is equal to X minus mu by sigma is another way to define the variable. Okay, and that variable is known as standard normal variate. That variable is called standard normal variate. What will be the form of its probability density function? Now you see, the probability density function for the normal variate was of the form this. Carefully look into this. 1 by sigma root 2 pi integration minus infinity to plus infinity e to the power minus this dx. Now when you write the variable Z in terms of capital X, like X minus mu by sigma, this is also a random variable which takes values of the form small x minus mu by sigma. Just like capital X takes the value small x, capital X minus mu by sigma will take the value small x minus mu by sigma. And if capital X minus mu by sigma is capital Z, small x minus mu by sigma will be small z. So we shall substitute in place of x minus mu by sigma z, and its d of x minus mu by sigma will be dz. So what do we get? We get integration minus infinity to plus infinity e to the power minus half z square dz. Z lies between minus infinity to plus infinity. 1 by root 2 pi is there. It is a constant term. It will be there. But where is sigma? Where does it go? Where is it gone? Sigma, how did it vanish? It's let me explain. In the examination, you solved a problem where I stated that I gave you this expression and I asked you to find variance of Z. I gave you this expression. Probably you can recall. And I asked you to find the variance of this expression. In place of Z, there was Y. And just now, a few minutes ago, we solved this problem and found that variance of Y is what? Variance of Y is 1. So here also, you can easily check that variance of Z is 1. So here in place of sigma, 1 is there. So it hasn't vanished. It has taken the value 1. So sigma has been written, 1 has been written. And what is the expectation of Z? You also proved that the expectation is what? 0. Expectation of the random variable Y is 0. Here also expectation of Z is 0. Okay, so in place of mu we have 0. You can say that it is 0. Okay, so what happens if I write the probability density function in this way? What happens is that if you take these figures, consider these figures, then suppose I'm considering this one, the origin of the coordinate axis is somewhere on the left hand side, somewhere here, and at 2 distance apart, I'm drawing my figure. Okay, I'm drawing it. Now when you consider Z, this origin, which is somewhere on the left hand side, it shifts its place and takes the position of here. So origin shifts. When I write the expression x minus mu, origin shifted to mu. And when I divide by sigma, the scale changes. It's the formula of change of origin and scale. The formula z equal to x minus mu by sigma is the formula of origin of It's a formula of origin of change of origin and scale. This is change of origin and that is change of scale. So origin takes the middle form. And when origin takes the middle, when origin comes here, analysis of the problems become easier. Because if origin is in the middle, origin is in the middle point, then we can say on the left hand side of the origin, on the left hand side of that, all the negative values are there for z, and on the right hand side all the positive values are there for z, and on the left hand side the area is 50%, on the right hand side the area is 50%, because it is a normal curve and it is bell shaped and it is symmetric, and total area is 1. So our problem, our calculation of our solving of the problems become easier if we do not talk about capital X, but rather we talk about Z. So we always discuss, we always consider the problems of the normal distribution with respect to the standard normal variate, not with respect to the normal variate. It's a usual practice. Here I have shown a pretty beautiful normal curve, but not in terms of z, in terms of x. How? Because on the middle I have written mu. If it were z, I could have written 0 here. So this curve has been shown in terms of capital X. But why this curve is important? Why have I shown this curve? To explain you something. What is that? You see, suppose I am talking about, for the time being, I am talking about the normal variable x. Now, for x, the mean is mu. Okay. Now, if you move sigma distance apart on the left hand side, you will reach to mu minus sigma point, and a sigma distance on the right hand side will take you to mu plus sigma point. These 2 points are equidistant from mu. And not only that, the entire region from mu minus sigma to mu plus sigma will contain 68% of the total area. Okay, and not only this, since it is a normal curve, this is the median, so it is dividing both the regions into 2 equal halves. So 0.68 will be divided by 2, that is 0.34 area is for the left hand side for mu minus sigma to mu, and for 0.34 areas for mu to mu plus sigma. Similarly, if we move 2 distance apart on both sides, we will reach respectively to the points mu minus 2 sigma and mu plus 2 sigma. And from mu minus 2 sigma to mu plus 2 sigma, the entire area is 95% of the total area. And similarly, for mu minus 3 sigma to mu plus 3 sigma, the entire area is 0.997. That is 99.7% of the total area is covered by this range. This is the biggest range, mu minus 3 sigma to mu plus 3 sigma. So this diagram can be represented mathematically in the following way. See, I have shown here. Probability that x lies between mu minus sigma to mu plus sigma. I have divided both sides by sigma, and I have done a little bit of simplification, and I obtained this. So in the middle I get x minus mu by sigma. On both the sides, in place of mu minus sigma I got minus 1, and in place of mu plus sigma I got 1. You can do the calculation by yourself. Now x minus mu by sigma becomes z by my definition. So actually 0.68 gives the area in terms of standard normal variate. We can say that 0.68 means the standard normal variate will lie between minus 1 to plus 1. Similarly, for this one, I can say that 0.95 represents the area that standard normal variable will lie between minus 2 to plus 2. And 0.997 is the area which appears for when the standard normal variate lies between minus 3 and plus 3. So all these areas which has been represented in the diagram has been converted with respect to the standard normal variate. Now, if we calculate from minus 3 to plus 3, the total distance is what? 6. Okay, from 0 to minus 3 it is 3 units apart. From 0 to 3 it is 3 units apart. So from minus 3 to 3 the total distance is 3. Therefore, this range, which contains 99.7% of the total area, that is mu minus 3 sigma to mu plus 3 sigma, is called the 6 sigma range. And 6 sigma range is very important in not only in physics, also in engineering. Let me tell you a story. Let me tell you something. Not a story, it is a fact. Almost in the last century, in the beginning of the last century, one particle was discovered by a physicist known as Professor Higgs. And along with our well-known physicists of Bengal, S.N. Bose. The particle was later named by them as Higgs boson particle. But throughout the last century, their existence of those particles were not proved. They couldn't prove that those particles actually exist in nature. But in this century, in the beginning of this century, when Large Hadron Collider was actually designed and it was actually planned. Probably you have heard about Large Hadron Collider. It is situated at CERN of Switzerland. So when it is designed, they're designed to know the origin of the universe. What is the origin of the universe? So they bombarded something, particles scattered, and there was this area was covered circularly. One particle moved in this direction, another set of particles moved in that direction, and they bombarded. And from those bombardments, many particles arose, and they are actually presently studying those particles. They are repeating the experiment and they are studying the particles to know the origin of the universe. And during this experiment, something amazing happened. What? They suddenly saw that Higgs boson particle came out. Okay, and they could identify it. They repeated their experiment several times. Okay, and they applied the 6 sigma scale over there. They took the statistics. Okay, they took the statistics again and again, and they, with respect to the help of the 6 sigma scale, they ultimately could come to this conclusion that Higgs boson particles existence is there, and Higgs got Nobel Prize for that. Now, what I mean to say, that what I say here in the classroom, I can prove everything what I say. So I'll suggest you a particular movie to you, which you can download. It's a documentary and its name is Particle Fever. This movie talks about everything which I have discussed. Okay, and you can download this movie and you can verify what I say. This movie is very interesting. And if you cannot download, when the college opens, you take this movie from me. I have this movie. Okay, so my point here is that Higgs and Bose, they were physicists, and they theorized the particle. Mathematics was done, but there were no traces of engineers. Now in the 20th century, the Hadron Collider, the experiment, all happened because of the engineers, because of you, not because of the physicist. Physicists can theorize, mathematicians can theorize, engineers can experiment. They have this power. We do not have this power. We do not have this facility. So it is all up to you. So some people think that engineering practice doesn't require the knowledge of physics. Physics give you the base, the pillar, and you implement it through engineering. Okay, so the people who say that mathematics and physics are not actually required for engineering students, they are dull. They are dull brain. Okay, so they know nothing. 85% people in Large Hadron Collider experiment were engineers. Electronics engineer, information technology engineer, computer engineer, mechanical engineer, civil engineer, instrumentation engineer, and you name it, chemical engineer, everybody was there. 1,000 scientists experimented on that. Okay, so what you are learning is being used everywhere. You have to know the theory properly. to get into that, to get into the system, and to do sometime, someday later, you will be doing the experiment by your own. So these theories are not dull theories. These theories are very much in existence. Their practical existence is very significant. Only that for our negligence we do not understand or we neglect it. So this was what I mean to say. Rest is up to you whether you want to continue with that or not. That is up to you. Okay. Now you see.
Hello, sir.
Hello. Hello.
Sir,
Yeah.
sir, we have another class from 4:10.
Oh, okay, okay. Sorry. So I am going to conclude right now. Tomorrow we are going to meet and we are going to continue with that. Okay. Thank you so much for informing me.